Okay, the recorder started. Good afternoon, everybody. I think you have already available all the videos of the previous two lectures. And if you see something missing, please let me know. And you can write me on the chat or an email is better. About the next lectures. I spoke with Professor Bratt. I wrote on the chat yesterday. He is willing to start at 2:30 for the next 3 lectures. However, he told me that I don't know when, but he will have a problem with one of the dates, and he will need to postpone it or reschedule it. I'm not sure. And therefore, he told me to tell one of you to contact him in order to take an agreement by email. And I wrote an email, the email address, which is not correct. And then he replied in the chat with the correct email address. It's better if he is contacted by one person speaking in Italian, writing in Italian. And so I'm not sure if you can take, okay, perfect. Yeah, it's just before next Friday. It's not urgent. And
we will talk with him about this next lecture, next Friday.
Yeah, but next Friday, I understood that he will be here at 2:30. But in any case, please contact him like on Monday, just to make sure, because this was my understanding, but we exchanged a couple of emails. I didn't speak with him. So I don't think he needs to reschedule the next one, but maybe the next. So just contact him and you will get the confirmation. I also checked that the room is indeed free also for the next lectures, next Fridays, so you can anticipate. But he told me that he would like to start at 2:30, but anyway, please check. Okay, perfect. And now let's go here, coastal engineering, and let's have a look at 1 second again at the theory, because I want to tell you a couple of things about the CRC equation. First, I am making some additions here in the theory, just some additional sentences to clarify things. So you may see changes. I will also change the date of the last revision at the bottom of the page, but now it's still not yet changed. So I wanted to tell you this. And if you see, because, you know, while I'm teaching, I realize that some things may be improved. So I'm making changes. If you realize that there is something more, don't worry, because eventually the things that you see more, because I am thinking of adding another formula besides the CRC. If you see that another formula is added for the exam, you don't need anything more of what we already discussed. Okay, just to make it clear, because I don't want to make you concerned. There is one thing that I wanted to tell you, which was not clear, and it's still not clear in the lecture. And I was stimulated by your question, by the way. And this is the thing. When we computed the energy flux per unit wave width, we assumed after the computation, and this computation is, let's say here, it is this one, this formula here. So there is this expression, which gives to you, again, the wave energy for unit width of the wave crest. And then we assumed that the sediment transport is proportional to this energy that we computed. So you may wonder, I said that the formula is dimensionally consistent because energy per unit width as the unit of a weight. And therefore, given that we equated this energy flux to a weight of sediment, this is dimensionally consistent. However, you may wonder, you may notice an inconsistency because the energy is computed for unit wave width, while the energy flux, the sediment flux, is just computed through a cross section of the beach. So you may wonder whether this is really physically motivated, because the energy is for unit width. And if I took a width that is 2 meters, so the energy is doubled, the computation of the sediment flux through the beach shouldn't change. Okay, perfect. I want to tell you that indeed, from a physical point of view, the formula is not consistent. The formula was derived empirically. It was derived empirically at around 1940. And they noticed that the flux of sediment, thanks to measurement, is proportional to the energy flux for unit width of the wave. So it's an empirical determination. It's not physically based. The fact that the units are consistent doesn't mean that it's fully physically based, okay? So when you introduce the coefficient K, which I said several references suggest to put it equal to 0.7, actually, if you take the energy computed in 2 meters of width, would result half of the value suggested of 0.7. It's just an empirical correspondence, okay? And then, in fact, at the beginning, when people derived this formula, they didn't try to give a physical explanation. They simply said the sediment flux is expressed as a function of the wave energy. And the wave energy usually is computed per unit width. Perfect. Now, you may wonder, you may be concerned by this kind of half physical explanation. Actually, it's take a fully physically based derivation. And then you have to transform the energy of the wave in bottom velocity and in shear stress. Shear stress, you mean friction, in order to compute the flux of sediments. And actually, with this full physically based explanation, we end up by getting a formula that is equivalent to the CRC equation. So indeed, it's an empirical equation that is confirmed by a physically based derivation, but we didn't make any physically based derivation. Is it clear what I added today, just now? So take it as an empirical formula, and don't be confused about unit width of the wave crest, okay? Don't be confused about that. I hope it's clear. And so I am thinking of adding the fully physically based explanation in my notes. But however, it's a little bit complicated, so I am trying to simplify it. And eventually, if you see it, don't worry. It's just something that I am adding in order to explain better how the CRC formula, the reason why the CRC formula is still widely used. Indeed, this is a formula that is still widely used. Even if it doesn't take into account the size of the grains, it doesn't take into account the shape of the beach, it only takes into account the wave behaviors, and in particular the wave energy, and the specific weight of sediments, but not the geometry of the sediments, the width of the sediment. And it's clearly motivated, it's clearly understandable that the sediment transport should depend on the type of sediments, on the type of sand or gravel or cobbles. It's clear. But the CRC formula doesn't take it into account. It is usually used in sandy environments and still widely used because it's quite reliable. Also, you may notice that in the notes now, the suggested value 0.7 for K disappeared. The reason why it disappeared is that I thought that giving a unique value is not really correct. I'm trying to add different values of K that are suggested in different environments. So basically, the behavior of the beach are in the practical applications included through the K value. So there are some tables in the literature which suggest, for instance, that in the presence of COBOLs, K should be reduced because the sediment transport must be reduced when dealing with cobbles instead of sand grains. So I also removed the suggested value of K, and my aim is to include a more refined explanation. Everything is, do you have any question? Okay, good. Now, you may remember that we started our exercise. So I propose that now we carry out the exercise because I want to complete it. I don't think it will take much time, but I want to get it done because this is our last lecture. And then I think we will have some spare time later, and I still have a couple of lectures more relaxing to teach. And one is dedicated to wave recording, and I'm sure that we will have time today to complete it. Wave recording means getting wave data, how they are detected, surveyed, and stored. And I have also last one lecture on nature-based solutions. It's very descriptive. I'm not sure we will have time to make it today, so in case we don't have time, I'll tell you what to do with this last lecture. Okay, so if you agree, I would open an R console and we'll try to move forward together with you. I am starting from scratch because you may remember that we just dedicated to the exercise 10 minutes. So I'm starting from scratch, but if you have any question, because I will up to the data loading, because last Friday we just got to loading the data. Okay, and this part of data loading, given that we already made it, I will make it very quick. If you have any question, don't worry, just stop me, okay? So let me share the screen. I forgot indeed to share the screen, but Gabriele, you didn't lose anything because I just showed the web page with the CRC formula. I'm sorry for that. Okay. Now, R, oops, sorry for that. Okay, good. R, let's take this figure here. So you may remember it's already installed here, unless somebody deinstalled it, removed it. No, it's here. So this is the R console. And just 1 second, I take a font that is a bit larger. Okay, good. I clear the screen with Control L. And remember, I have the data in the links here. There is the text of the exercise. We don't read it again. And we have also the data file in this zip file here. Okay, this is the text. And you may notice that I changed the web address with the links of the data files, just in order to update it. And then I have the data files of the geometry of the shoreline. I just want to show to you them on the screen. This is geometry of the shoreline, which we already uploaded last time, wave forcing, and here we have the suggested R file. And I wanted to take it on the screen because just 1 second, it needs to load. Let's see. Okay, it's here. 1 second. It is opened in Notepad. Sorry. Okay, here is the console. 1 second, because I made some. Okay, here is the console, and let me put both windows on the screen. The window of the suggested R file. Okay, here it is. Good. 1 second, I want to resize it. Okay, good. Okay, here we are. Perfect. And now, let me just check in Windows if data files are still in the desktop. So I take a file manager in Windows. So. Okay, here I am. Sorry for that. And let me check on the desktop if everything is here. Yes, I have indeed the two files of the data, cost and wave forcing. So I can go in the R console and in the data file, I think now I have just to copy these instructions. Copy and paste them here. Sorry. I forgot one thing. I forgot to set the directory on the desktop. Change directory, desktop. Okay, now I am on the desktop and I can paste the instructions. Good. You see that everything is okay. I just wanted to draw your attention on this latter because we commented already all of these instructions. And I just want to comment on this last one. Okay, it's a transformation from a vector to an array. So let me just open a parenthesis in order to clarify what I did. So let's suppose that we create a vector. Let's call it temp v. If I put the uppercase for v, this needs to be then kept in mind. And let's create a vector with the instruction C. The function C is the function in R to create a vector. And then as an argument of the function, you need to put the elements of the vector. So let's put the 1, 2, 3, 4. So it's a vector with 4 numbers inside. And if we make if we print the vector on the screen, indeed you see that you get 1, 2, 3, 4. Now what I did as the last instruction of the exercise is to transform this vector into an array. So the instruction to transform, to create an array by using a vector has input data for the array, I need to decide the name of the array. So temp m or temp a for array is equal array. And then if you want to use a vector, then you may give the name of the vector and then the dimension. And the dimension is to be given as a vector. So dimension equals C to 2. This is the result, temp A. This is the array. So this is the explanation of what I did. And just beware that I could have overwritten the vector. So if I use the same name for vector and array, so if I had printed this instruction, so same name for the array that I am creating and the vector that I'm using to provide the data, then what I obtain is an overwrite of the vector. Good. And you may have got the same result by typing temp v equal array, and then C1, 2, 3, 4, dimension equals C2, 2, and you get the same result, you see? Good. The array may be transposed, so temp v equal T temp v. Visualize temp v, it's transposed. This procedure of getting the data from a file in the form of a vector, and then, if needed, to transform it into an array, it's usual with these programs, and in particular, usual with R. Good. Just keep in mind one thing. Let me start from scratch and let me write temp v equal a vector of 6 elements, not 4. Okay, 1, 2, 3, 4, 5, 6. Good. And then let's create the array temp A equal array temp v dimension equals C32. Good. You have to pay attention when you specify the dimensions to your result, because if now you visualize the array, you see that it goes by columns 1, 2, 3, 4, 5, 6. 1, 2, 3 is the first column, 4, 5, 6 is the second column. You may want the data following the rows, not the columns, and therefore the dimension has to be inverted. Dimension 2, 3, not 3, 2. And now you see that the data still follow the columns, but you get rows that are 3 numbers long, but the data still follow the columns. So if I want the data in ascending order following the rows, what should I do? Good. So given the result of my previous experience, what I would do is temp A equal to, I get back the first instruction, but I put a transpose here. So what is the result? Temp A. Now I have the data following the rows 1, 2, 3, 4, 5, 6. What is the moral of the story? Why I dedicated some time to making these attempts? When you deal with matrices, pay much attention. Okay, rows, vectors are easy to manage. Matrices are a bit too, a bit too tricky. And it is very simple. What I did is very stupid. It's simple. But remember that when you make complex works, complex elaboration, usually you it's more likely that you make mistakes in the easy steps than in the complicated steps. So pay attention to those steps that look very easy to you. These are the tricky ones. This is the moral of the story. Okay, now let's go back to our previous, to our exercise. But before moving back to the exercise, I want to remove the variables which I created in order to make these attempts of data management. So let me make a list of variables. These are the variables which I have introduced so far. So let me remove with the instruction rm temp A and temp B. Let me check. Now I have only the variables which are pertinent to the exercise. Okay, very good. Okay, let's move forward, and therefore let's go back to the file. And you see that indeed I transformed a couple of vectors into arrays. I have the array PR1, which gives the coastline geometry, and I have the array PR2, which gives the wave forcing. Okay. Now here, for the sake of clarity, I prefer to decompose these arrays into individual vectors for the sake of clarity, just for the sake of clarity. Okay. So in order to decompose the arrays in, let's try to do the first one. Let me copy the first instruction here. Copy. In order to decompose, sorry, the first one. Here I created a vector XLC, which is the position of the coastline. And the vector was created by taking a column from the array PR1. So you see here, I got the first column.
Index in R starts from 1, right? Not 0.
So index in R stays 1. Yes, yeah, not 0. So for instance, if you look at PR1, this is the position of the coastline, and the first column, and the second column is instead the limiting position. So if I want to get the first column from this matrix PR1, 1, comma, get here the position of the coastline, and the limiting position is in the second column. You see that it should be always lower. Indeed, it's always lower. Okay, we may plot the position of the coastline just in order but before plotting, let me now get the other variables. I'm clearing the screen. Okay. Let me get the other variables. You see here that there are several instructions that aim to extract the columns, the individual columns from the matrix PR2. And these individual columns give to you the position of the breaker line, which is not interesting for us. We are not using it. The wave height at the breaker line, this is interesting for us. The wavelength at the breaker line, it's not interesting for us. The sea bottom depth at the breaker line, this is relevant. And the wave angle, this is relevant to, this is also relevant. So let's try to get these columns. So I copy these instructions and I paste them into R. And here it is. So if you take DLF, this is position of the breaker line. HB is the wave height. It's about 1 meter. Wave height is twice the amplitude, just beware. And the sea bottom depth, just to get an idea, about 1 meter. 1.5 meters. Okay, good. As I said, we could now plot the coastline, the geometry of the coastline. Why it's interesting to plot it? Just to check if it's something meaningful. Okay. So in order to plot it, we need to create the vertical axis, the vertical coordinates, the y coordinates. You may remember that in the description of the geometry of the coastline, the ordinates are equally spaced, and the delta between the difference between one coordinate and the next one y, and the next y is fixed 150 meters. And it's the coordinates on the horizontal axis, which are not equally spaced, of course. So let's create, given that we have 20 points, let's create the coordinates of the y-axis. Through cum sum and repetition, let's try to see what is rep. Rep is a function that repeats a number. So I can repeat 3 5 times, and this is what you get. And cum sum is the function that takes the cumulative sum of a vector. So cum sum rep 3 5 is 3 6 9 12 15. Perfect. So the y coordinates, you remember that the dy was equally spaced at 150 meters, as I said. And let's see. Y. This is what we obtained. Okay, now here there is an instruction to duplicate the coordinates of the shoreline. So let me copy and paste it. Why the shoreline is duplicated? Because the shoreline is going to change, the geometry of the shoreline is going to change. So it's better before changing it to keep memory of the original position. Just that. And now we can make the plot. So how to make a plot? So first of all, let's make a very simple plot. A plot is made in R with the instruction plot. It's not really a lot of creativity. Instruction plot, and then plot wants the vector of the x first and the vector of the y. So let me make the plot of two vectors, just 1, 2, 3, 4. This is the x, and the y is another vector, and maybe 4, 5, 6, 7. This is the result should be a straight line. Let's see. Yes, you see that it's a straight line. It's visualized with, points. I don't like points. Just let me go back to it. Where is? 1 second. Okay, here it is. So I don't like points. Let me make it a line. So I get the instruction back with the arrow up. And then before closing the parentheses, I write type equal line. It's a straight line. If you see the input data, you are indeed expecting a straight line. Okay, good. There are several other options, like let me get again the plot and let me put a line width, which is 3, and then you see the line width was increased. You see that the titles of the axes are automatically included. Good. Now, if I want a different color, I get back the instruction and I add a col equal red. You see the line in red and so forth. Good. There are several options, as I said. R allows you to make very high-level graphics like MATLAB. It's very high level. So I think it is worth learning how to make high-level graphics. It is worth learning because when you present your results, if you can produce nice graphs, it's really much, much better because the convincing power of your presentation gains a lot. So it is something that I tend to suggest to students. Learn how to use photo editing because photo editing allows you to embellish the graphs even more. So learn how to use a high-level graphical high-level program to make graphics, to make graphs, and learn how to use photo editing. It's because it allows you to improve your presentation. And this is something that is becoming necessary also for scientific papers. And in order to, it's more likely that they get accepted if they are more convincing, if the graphics is well done. There are a lot of mosquitoes. It's tremendous. Yeah. Okay, now I just want to give you an example of a graph that can be made into R. Let me see if I can make it quite easily. Drive. Give me 1 minute, and then you should succeed. Mm-hmm. Mm-hmm. Okay, just 1 second. I want to show you a couple of images. No, this one not. And here. Mhm. Should be able to find it. Okay, here it is. Mhm. Mhm. Okay, it seems that it's okay. So this is an example. This is a graph that has been made with R. It's an animated figure. It's a regression line that is moving along a time series. And I'm not explaining, it's a river flow time series. And while the regression line moves, the slope of the regression line is visualized. And now another one. Let me see, maybe this one. It's a bit, anyway, I don't want to take you out. Okay, here it is. You see, it's an animated figure. It's rotating in order to show this surface from all the angles, the point of view. It's created with R as well. It's not the final one because in the final one I changed the colors, and you see that while it's rotating, the captions are a bit superimposing over the title, which is not a good thing. Anyway, this is just an example to give you an idea. Let's keep this here because I just wanted later on to show you other things. So let me just. Back here. So we got the plot. Now let's, but this is an example plot. Now let's get the plot of the coastline. So let's take our file here and let's take this plot instruction. Copy it, I put it into R. So you see that there are some options which we still don't know. Let's gate the graph first and there is something missing. Just 1 second. Don't understand why. Yeah, because I forgot to copy this. So let me copy this instruction, which I forgot to copy first, and now I get the plot again. Okay, here is the plot, and this is the coastline, which is still, let me see. Okay, lines. Yeah, I forgot to put the limiting position. It's here. And now you see also the limiting position. As you see, the vertical axis is equally spaced. The horizontal axis is set by coordinates. Okay, here we are.
Yes.
Yeah.
In the X direction, what did we update the data in cell phone or was it?
Okay, it's XLC old.
Okay.
It's a copy of the position of the coastline. Just 1 second, I get the instruction. see here, I made a copy of XLC. XLC is, 1 second. I'm getting, you see, the XLC is the position of the coastline as it is given in the file. Okay. So, okay, now we are ready to start. And what do we have to do? Just to make it clear. So let's look at this graph with the position of the coastline, okay? And I try to make a copy here. Let me take the black pen. It's something like this, okay? On the blackboard, I have less points. So with the black dots, I highlight the limit of each segment that defines the coastline. Remember, we are presenting the coastline as a sequence of pieces, okay? As a sequence of coordinates. So we are discretizing the coastline into chunks, those one, okay? So, and this is the situation at t equals 0. Now, let's, and we also have defined the delta t, which is 120 seconds. Now, let's go to t equal 1. So t equal 1, which is equal to 0 plus 120 seconds. Okay. Now, at t equal 1, and we have to perform, I don't remember how many, I think something like 100 simulations, a long time, I don't remember, but it's written there, okay? Now, at t equal 1, we assume that the position of the coastline is changed, and therefore we have to determine the new position of the coastline. And this is the first simulation time step. Okay, time step, first one. How to compute the new position of the coastline? What we do is to compute the segment flux getting into here. And we compute it as a function of the wave height here. Okay, perfect. Now, and this is the first spatial step. So we are within the first time step, and we compute, depending on the wave height, blue arrow, in the first spatial step, we compute the first flux. Good. Now we go to the second, and let's suppose that we compute here the second spatial step. Let's suppose that the wave height, the wave energy is lower. This is why the arrow is shorter. And then the sediment transport is lower. Okay. Now, what happens then within this first chunk? I have a high income of sediments and a low outcome. So I assume that this one moves forward here. I keep the first one there fixed because I don't have any way for computing erosion or accretion here at the beginning. This is a feature of numerical discretization. When you are in the first step, you compute the delta for the next step. So we leave the first one here, unless we have boundary conditions. We may have boundary conditions, which means that you are informed by other means how to move this point, otherwise you leave it there. Okay? So basically, what you do is to bring the new coastline here. And the first spatial step of the first time step is completed. So you have two cycles nested one into the other. Okay, you have the spatial step that is nested into the time step. So what we have to do is two cycles of simulations along the spatial steps for each time step. Okay, now the second spatial step may bring this point here, and therefore you do it like this, and then you get here like this, and then you get here like this. The number of spatial steps is equal to the number of coordinates of points minus 1. Now, at this stage, when we get here, when you get here, the first time step is completed. And then you can start with the second. And then with the second time step, you may get this one here, etc. Okay. Good. Now, you may adopt different numerical schemes. What does this mean? First of all, you will see in our exercise that I am computing the sediment transport over two neighboring chunks because I want to smooth the computation. I want to get a smoother result. This is one trick that I do in the numerical computation. Also, here, I said that in the first spatial step, I used to compute the sediment flux, the wave height here. There are numerical schemes that use the average wave height at the extreme of the chunk. So instead of computing what happens here as a function of the only wave height at the beginning of the step, I take the average wave height and then I compute an average situation. Another solution may be you compute the average, the sediment flux depending on the wave height here, and then the sediment flux depending on the wave height here, and then you take the average of the two sediment fluxes in order to understand what happens within the first chunk. This is a different scheme. It's not the same thing. If you compute the sediment flux for the average of the wave, it's not the same thing as averaging the sediment flux computed for the individual waves. Why it's not the same thing? Because the relationship is not linear. So you may wonder how to decide these tricks, these numerical computations, and is it wiser to take the average wave behavior, or it's wiser to take the average of the sediment fluxes? It depends on the computation that you have to make. There are some schemes that are suggested by the literature. There are some schemes that you may invent yourself. And you have to pay attention to the fact that when you make a numerical computation, you always have an approximation, always. And the approximation depends on the numerical scheme that you use. And depending on some features of the system, of the computation, depending on the features of the computation, the errors may explode. They may sum up and the solution may diverge. This is why the literature suggests some numerical schemes, because some schemes are stable, some schemes are not. Stability means that the error does not diverge. This is a kind of a problem that is not very complicated. It's unlikely that the errors here diverge unless you make a simulation that is very long. And if it's very long, like instead of having 20 coordinates, you have 1 million coordinates, then it may happen that there is something that goes wrong. But in general, this is something, I mean, that gives it to you flexibility. Whatever the result, you shouldn't get meaningless outcomes. But you have to always check. I don't want to get into the details of numerical computation for two reasons. First, I'm not an expert. Second, I think you may have had some background in other courses. I'm not sure if you if you had lectures of numerical integration or finite differences, numerical schemes, but I guess yes, it's very likely. So maybe that you are more prepared than me. So I don't want to get into the details here. I just want to tell you that the scheme that I used here, I borrowed it from a suggested exercise that I found in the literature, but it's very, I mean, it's very simple. And there is a lot of flexibility. You may try to make changes and see what happens. Here, the most complicated thing now is that we have to start 2 cycles because, as you have seen, we have an integration sorry, not an integration. There is a routing in the space and a routing over time. So you have to start 2 cycles. What is a cycle? Okay. Within coding, what is a cycle? So each programming language has 2 essential features: cycles and conditions. If you want the computer able to decide, based on the results that the computer takes, you have to fix conditions. Like if the result is less than 0, then take another computation, then do that. If the result is greater than 0, then do that. This is a condition. And the cycle is an instruction that allows you to repeat the same computation many times. And this is what we need here, because we have to repeat the computation of the sending and delivery over space and over time. So we need cycles. So when you learn a new programming language, the first guideline is to learn how the language wants cycles and conditions to be written. Okay, so into R, how can we write a cycle? You may look to Google and look R, cycle, etc. The instruction is for, and this is a typical instruction for several programming languages. For, but still we need to know how to use it, how to type it. Other programming languages use the instruction do. There are some variants, and if you know other variants, MATLAB, what is the instruction for the cycle? For? Yeah. So you see, MATLAB is quite similar. For is very common. I think it's also used in BASIC. I'm not sure, because I also learned BASIC about 30 years ago. I don't remember it anymore.
Also in Python or in JavaScript.
Okay. Okay. Good. Okay, let's start the cycle then. And first of all, we need to define a vector into R. Remember that R doesn't want variables to be defined. So into R, you may write A equal to, which means that you assigned a variable. And without defining it first, usually, this is not the case for several programming languages. Usually, a programming language wants any variable to be first defined, okay? And this also happens for vector and matrices. And R doesn't want a variable to be defined, but R do want vectors to be defined. So let's suppose that let me give you a demonstration. Let's suppose that I want to create a new vector. And if I want to create a new vector, what I can do is to do like this, equal C0. This is a new vector. And only the value 0. Now I can write new vector index 1 and it says 0. If I write new vector index 2, it says nothing, but the vector is defined. Now, if I don't define the new vector and I write new vector new 1, it says I didn't find anything. So I cannot write new vector new 1 equal 1 because it needs to be first defined. So it's different with respect to what I did with the variable. The variable, I defined it directly by giving the value. Vectors, I cannot give just the value. I need to define it first with the instruction C. Okay, now let me remove these variables. Vector 1, new vector, and new vector new. No, new vector new was not defined. Here, let me see a list of the variables. Yeah, sorry. It was A, not 2. Okay, good. Okay, now let's look at here. Let's define the vector, sorry. I made a mistake. Let's define the vector QL then. What is QL? QL is the vector of the sediment transport. And it is defined in this way with the function repetition. This function means that I am creating a vector named QL by repeating 0 20 times. So this is the result. This is QL. QL, again, is the sediment transport. A sediment transport which can be computed 20 times because I have 20 values of wave height, sea depth, etc. Perfect. Now we can start the spatial cycle. But and the spatial cycle includes 19 computations. But let me just first make a cycle to smooth the coordinates of the coastline. This is one of the tricks which I mentioned to you before. So I'm substituting each coordinate of the coastline with the average of each coordinate and the next one. So you see this instruction. Basically, what I do is to write XLCI, where I is varying from 1 to 20, is equal to XLCI plus XLCI plus 1 divided by 2. I'm taking the average. So basically, if I have a cost line that is that goes this way, what I'm doing now is to take this point and put it at the average distance between this point and the next. And then I take this and I put it at average distance with respect to the next. And same thing here. I put it at the average position, which remains, given that this is horizontal, remains like that. And you see that the result is smoothed. I am regularizing the coastline. Of course, I cannot change the position of the last one because I don't have the next point. Okay, so I can make this smoothing in this way. First, the fourth cycle. Look how is the syntax for, and then between parentheses, you have the cycle variable. I decided to use J here, which is varying between 1 and 19. If you type return, you see that the console is waiting for your input, and then you need to set the instruction that is to be repeated. If the instruction is a single one, which is the one that I am selecting here, you can just type it directly. And that's it. And if you have several instructions to be repeated, you have to use the curly bracket. The several instructions must be included between curly brackets. How to type the curly bracket, it depends on the keyboard of your PC. Usually what I do to get the curly bracket, let's see if it works here. Let's see. Doesn't work. Just 1 second, I'm trying several solutions, but usually what I do is to press at the same time Alt-GR, which is the key on the right of the space bar, plus, but it doesn't work here. Just 1 second, I try again. No, it doesn't work. Let me check if there is another combination. Don't find anything. Just 1 second. Let me try something more.
For me, it's Alt-GR 7.
Alt-GR 7. Yeah, this is also in my keyboard in Bologna. Here it doesn't work.
I think it's Majus, Alt-GR and square parentheses.
Majusc Alt-GR square. Good, great, in Windows, yeah.
What can I ask? When we use 1.19,
Okay,
does it give the last, the last return of this is 19 or 18?
you said so
1.19.
1,
one, not that, this one.
Ah, okay, yeah.
19. The last one is 19 or 18?
No, it's 19.
It's 19.
Yeah. You can try, for instance, for II in 1, 2, and then you may write the instruction cut is an instruction to print on the screen. And if you put fill equal true, it goes to a new line. And you see here, okay? Yeah. Okay, so now we can start the cycle from I in 1, 2, and delta t. And this is the cycle along this time steps. So I is the indicator of the time step. Okay, just 1 second. And now we open the curly bracket. We open the curly bracket, and the cycle is executed when I close the curly bracket. And now what I have to do is the cycle along the spatial step for II in 19. Okay, Y19, sorry, Y2, because as you will see, I want to take another average later on, and I need to start from 2. And I'll tell you why when we get to the instruction. Now just note that we are starting from index II equal to 2. And again, you will see why we need this. Another curly bracket. So now we are inside the spatial cycle. Okay, what I want to do now is to make another average of the shoreline coordinates. Why another average? Because I already smoothed the shoreline. Why another average? I am taking another average. As you will see with the instruction, what I am doing is to take another average coordinate. I'm doing this because if you remove this instruction, you may try also to remove this. If you remove this instruction, the result would be too much oscillating, too much variable, you know. So what I'm doing is to compute an auxiliary value of the x coordinate of the shoreline, which is the average between the two neighboring coordinates. So this is equal to XLC II plus 1. Yeah, if you can close the door, yes, would be great. Are you closing the door?
I have to go and come back.
Yeah, sorry.
But if you want, I can close it.
Yeah, try. Let's see if it's less noisy. I don't think it changes much because it's open up there. minus XLC II minus 1. Okay, I was not clear enough because now I realized that indeed here I'm not computing the average. I am computing this thing. Let me make a sketch here. So let's suppose that we have the coastline which is displaced in this way. And I want to compute the wave angle. The wave direction is given for each point here. So it may be here, it may be here. Okay. And what I need to do is to compute the angle between the wave and the shoreline, between the wave direction and the shoreline. So given that it's unlikely that the angle between the wave and the shoreline is much variable, is much varying, what I am doing here is to compute the angle by drawing a straight line between the 3 points. This is what I am doing. In fact, you see here I am computing an auxiliary x, which is given by the difference between the x here and the x here. And then what I compute is the wave angle here. And the wave angle is computed by referring to the wave direction in the middle point. So what I'm computing here is this angle. Now I am making the sketch. I am remaking the sketch. Let me delete this one. So what I need is the wave angle between a given wave direction and the coastline. Okay, so let's suppose that we have a coastline that is oriented this way. Okay. First, I start from II equal to, which is the middle point. Remember that for each point of the shoreline, I have a wave direction. The wave direction, note that cannot be radically changing between one point and the other. So what I'm doing is first connecting the previous point, and this is II equal 1, and this is II equal 2. So I am connecting the 2 points. So I'm referring to II equal 2 to this point. I am connecting the coastline between the 2 neighboring points, and I am computing the wave angle with the wave direction in this point. And this is what is called here alpha 2. In order to do this, what I do is to compute the variable XLC aux, which is the difference between the two x coordinates. And then here there is the computation of the angle. Oops, sorry. Here is the computation of the angle. Let me show you one figure which can be taken from the text of the exercise. Okay, this figure is what gives an explanation of what I am computing. If you look at this figure, look at the screen, the dx here is precisely XLC aux. I go back to the figure. Let me just do like this. Okay. So dx is XLC aux. You see, it's the difference between x coordinates. dy is 150 meters, is the step during the y direction. Actually, here I have to take two vertical steps because I'm working on 3 points. I have to compute the angle alpha 2. Okay. Alpha 2 is given by the inverse tan. You can compute alpha 2 according to this relationship, and let me explain why, okay? Again, what I need is alpha 2, is the blue angle here, but if you read the text of the exercise, what I am given as an input data is the angle alpha of the wave direction. So the input data, I repeat, gives the angle alpha. The input data give the wave direction by giving the angle with the vertical axis. So what I know from the input data is alpha. Now I can compute alpha 2. Okay, alpha is replicated here. You see my mouse. This is alpha. So alpha 2 is equal to alpha minus alpha 1. Alpha 1 is replicated here. Look at my mouse. So what I have to write is alpha minus alpha 1. Alpha 1 is given by the inverse tangent of delta x divided delta y. So what I'm computing here is alpha 2, which is precisely what I need to compute. This is the main difficulty in understanding this exercise, and this is why I wanted to make such a draw that you find in the text of the exercise. This is the main problem, to compute this angle. It's not really complicated conceptually, but still, you know, when you make a trigonometric calculus, it's not easy. Okay, now what I'm doing is computation of the average wave height in the 3 points. So it's HB, an auxiliary value for HB. I take the average along 3 points of wave height in order to get a smoother result. And now I can compute EB and EBW. EBW is just the product of EB, which is the energy per unit horizontal area, times the group velocity. And now I can compute QL. And now I can close a curly bracket. Still, I have another for cycle, which is a long time that is still open. And now I can compute the difference between I can take the derivative of the vector QL, which is given by the differences between each element of QL and the next one. Basically, I am comparing sediment flux at the beginning of each chunk and the end of each chunk. So this vector is given by the difference. Take into account then when you take the difference of a vector, the differences of a vector, the resulting vector has the size of the original one minus 1. And now what we have to compute is the advance of the coastline or retreat of the coastline, the shift of the coastline. This instruction here, let's take it for granted for now. And I will explain a little bit when we make a break now. After the break, I will explain to you, I will provide to you the justification of this relationship here that allows you to compute DXC. DXC is the shift of the coastline along the y direction. So let me copy these instructions. Okay, and then I need to compute the new position of the coastline, and then I am done. Because DXC is the shift of the coastline. If I want to get the new position, I have to get the previous position plus DXC, and I overwrite the previous position. So each time step, I overwrite the previous position. So in this way, I am sure that when I repeat the cycle, I'm still updating the previous one. Okay. And now I need to close the two curly brackets. Okay, let me take it here because for some reason. So when you close the last curly bracket of a cycle, it is the time when you get error messages if you made mistakes. I didn't get any mistake here, so it looks like the computation is finished successfully. Okay, now let's make a break. Do you have any question?
Yeah, just thinking about this. I was trying to find a PowerPoint that showed last lesson.
I use the PowerPoint, just 1 second.
Well, some slides, I think.
Let me check, just check. Beach hydrodynamics and growth.
The one from the formula. For the formula.
For the former. This one? I think should be there.
I didn't also found them this side. Oh, there, okay.
Okay. It's in the bottom. The PowerPoint, when it's present, it's not always present. When it's present, it's at the bottom. Okay. Yeah, no problem.
But I copied all of the codes to the Python, and I managed to do it twice lowest.
Okay, so you did it in Python.
Yes.
Now. Okay.
Why I didn't understand the lowest. The
Yeah,
function.
I tell you. And I am interested in getting the code. And
Yeah, I can.
okay, you can email or put in the chat because I don't think it's long, but better an email.
Okay, but I used the Jupyter notebook.
Sorry?
Jupyter notebook.
What do you mean? I don't understand.
Jupyter notebook.
Okay.
I can share the Jupyter notebook file, and if you just search on Google, it's so easy to run.
Okay, okay.
It's run on the browser.
Okay, perfect. Now I understand. Sorry, because I don't know this tool. So, but I am interested in getting the code. Yes. Okay.
I'm sharing.
Yeah. Thank you very much.
What one's close?
Yeah, lowest. I tell you what's lowest. So, yeah. So the last instructions, it's what you find here in the R console. So lowest, it's a smoother. So first, let's look at the result, and then let's try to visualize the result without lowest. So you understand what is a smoother, which is, I think, understandable from the term, and how it works. So first, let me show you the results. And this is the instruction lines. Let me make it larger. So the blue line is the new cost line. Okay, so you see that there is some accretion, there is some erosion, and it's in principle, the balance of sediments, it's not necessarily zero, the balance, because you may have some more sediments getting in or some more erosion getting in. But, given that after a certain distance from the boundary, so a certain distance from the boundary on the left, you should find more or less a balance of sediments. And so let's try to remove the lowest now and see what is the change, because lowest is an instruction to smooth the result, which means to make the coastline more regular. First, take into account that I talked about the balance of sediments. In view of the numerical approximations that we did, the balance, you shouldn't expect a balance that closes exactly to zero. Besides the effect of the boundary conditions, there is also the fact that there is an approximation. And in particular, the lowest function may alter the balance of sediments. But let's remake this graph, but with the blue line without lowest, okay? So let me remake the graph here. I take the two instructions that I used to make it. Now we have only the original position and the limiting position. And let me remove the lowest instruction. So let me just copy this. I put this into R and I just delete lowest, okay? Okay, sorry. It's, it is correct. I have also to remove this argument here, which is an argument of lowest. Again, there is something more to remove, lines. Let me see, XLC. One plus, okay, cold blue. There is a comma.
The first parenthesis.
Let's see. No.
And also the other one.
No, there is a comma which is, let me see. Or maybe.
Yeah, that one and the other one, I think.
Let me just. XLC, Y. Okay, let me get the original. Sorry. Okay, here. Okay, so let me remove this lines. Okay. Ah, yeah. This one. How it should work. Let me see. Okay, good. So you see the result here. It's a little bit too much oscillating, and there is an effect of a boundary condition at the beginning, which makes you see that the figure is more balanced in terms of balance of sediments. You see that this is more reasonable, but it is too much scattered, let's say. And so let me get the instruction lowest back. This one. Lowest is a smoother, as I said, and the power of this smoother, it's, first of all, let me put a parenthesis here. I want to see if it changes something. No, this is like before. Okay, the power of this smoother is given by the parameter f. So let me get back the plot without okay, now the plot is just as the beginning, and let's put a smooth with f 0.1. And here it's still, just 1 second, let me try again. .3. It's a bit smoothed, but still it's still too scattered. Let me just now try 0.45, color equal orange. And this is much smoothed. So the power of the smoother depends on the parameter f. But you can also obtain smoothing by taking a moving average. So if you want to put it in the Python code, you can take a moving average. Otherwise, you can simply compare your result with without smoothing. This is not correct. Just 1 second. And let me put here, okay. Now the plot is this one, and then we take the lines without lowest. You can compare the outcome from Python with this one.
Probably I had a slight mistake because my grammar is not.
Okay. Maybe that the mistake is mine. I'm not sure. We can try, we can check. This is why I wanted you to send it. And this one should be tested. But this one was translated. I found the software on the web, and it was one of my colleagues in Sicily who prepared this. And it's I think it is correct, but I translated it from Fortran, which is another programming language, which is obsolete now. And you know, I may have made some mistakes. Just let me show you one thing. So OneDrive is still open. I want to show you the original file from my colleague, the original figure from my colleague. They applied actually this approach to a real coastline in Sicily. And I'm not sure. This is the PowerPoint from my colleagues. It's in Italian, so I apologize. I think there is the figure here. Yeah. So this is their coastline, and this is a real evolution of the coastline. And here, I think, no, it's a real evolution during time. And this is the model that they did. Anyway. Okay. Okay. 1 second. Okay, I want to open this directory because I want to show you a couple of videos later. Okay, there is still one thing pending. So first of all, I think you may still be a little bit confused because the code is a few lines of instructions, but still it's not easy to be understood online. Online meaning during a short frontal lecture. But it is commented, and if you are interested in expanding your knowledge like he did because he tried to translate in Python, I think it's a useful training. This is not information for the exam, so don't worry. It's just for you, but it's during the exam you will not have a question related to the practical application of this model. There is still one thing that we have to discuss, which is the computation, according to this instruction, just 1 second, of the Xi. Okay, we said, let me just give it for granted and then we discuss it. Keep in mind that here there is a DQL, which is the difference between incoming and outgoing flux of sediments. Flux means volume of sediment per unit time, okay? And here you see that this difference is computed by is multiplied by the time step. So if I multiply the difference between incoming and outgoing in flux, which is volume per unit time, I multiply it by the time step, I get the change in volume in each spatial step, in each chunk, okay? Now, let me get this figure, which I already showed to you. It's in the bottom of this lecture. This figure here, okay? And here you can see how the Xi, which is this quantity here, look at my mouse, is computed. Check if I'm still sharing the screen. Yes. Okay, so I have flux in, flux out, difference computed, multiplied by the time step, and this is the change in volume. The change in volume is the yellow volume that you see here, okay? The cross section of this volume is a parallelogram. So if you multiply the area of the parallelogram, which is given by delta Xi times the closure depth, which is the C depth at the breaker line, times delta Y, you get precisely the yellow volume. So delta Xi is given by yellow volume divided by delta Y divided by closure depth. Okay, so difference in flux times delta Y is the yellow volume, and times delta T is the yellow volume. Delta Xi is given by yellow volume, which is different in flux times delta T, divided by closure depth, divided by delta Y. So here, what we have is precisely difference in flux, DQL, times delta T, yellow volume, divided by dy, divided by closure depth. Okay, so this is how delta Xi is computed. Of course, you may say this is not precisely a parallelogram because these lines are not segments, but they are curves actually. but of course we accept approximation. We tolerate approximation, okay? Good. Any question? Okay, now we close the exercise part. We have 1 hour, a little bit more than 1 hour to go. Let's move forward with, let's call it theory. So first, we discussed so far a long-short sediment transport. And the method that we studied, the one-line model and the CIRC formula, CERC formula, they refer to the long-shore sediment transport. We mentioned that we also have to deal with the cross-shore sediment transport, which is relevant as well. And we also mentioned that there is a difference in time scale. We said that the long-shore sediment transport is responsible for the long-term changes, while seasonal changes, short-term changes are mainly caused by the cross-shore sediment transport. We don't describe in detail analytically the change in morphology caused by the cross-shore sediment transport, but I want to discuss it in a qualitative way, just to give you a feeling of how we should expect the forms of the coastline to change after a cross-shore sediment transport. And to this purpose here, there are some sketches, and these are handmade because I couldn't find, I found very nice sketches on the web, but I couldn't use them because they were copyrighted. So I reproduced them by hand. The problem is that by hand, I'm not a good drawer, and therefore I'm not good in drawing by hand, and therefore the quality is not excellent, but I hope that you can understand the concept. Actually, I made it by hand before the pandemics. After the pandemics, I could reproduce them in a better way because with the graphic blackboards that now every teacher has, it's very easy to reproduce figures. So if you look at the quality of the figures in my lecture, you can understand the difference between and after the pandemics. So as sometimes we say, we must be able to profit also from the crisis. So anyway, let's see what happens typically after a storm. After a storm, you get an erosion of the berm and the dune maybe. Especially if the storm is very extreme, then you may have also an erosion of the dune. The dune is built by the extreme storms, but if you get a storm that is more extreme with respect of those who built the dune, you may get also an erosion. This is why dunes are moving and berms are moving, because they are created by a certain marine weather, and they may be eroded by more extreme marine weathers. And you may also find several dunes because they are the expression of different time scales and different types of storm. I say different time scales because when we say more extreme, it means less frequent. So it means a longer time scale. Remember, more extreme means less frequent, which means longer time scale. Ordinary regime, an ordinary dune, is shaped by events that occur more frequently in the shorter time scale. So if you find more than one, closer to this coastline is created by events that are not as extreme and happen on a shorter time scale with respect to the dunes that are located more landwards. Okay, so this is what happens after a huge storm. So part of the berm and the dune may be moved into the sea, and this is why beach scrapping is done during the winter, on the Adriatic Sea, for instance, what they do is basically, in the Adriatic Sea, where the beaches are maintained, you don't have dunes. Okay, in order to see dunes, you have to go on a free beach, a beach that is not maintained. So, but in a beach that is maintained, usually, if you look at the cross section of the beach, we take the black. You can see usually during the summer a shape. I am exaggerating the slope like this, and then you have the berm, and then you have the sea and the bar. So usually it's something like this. What they do during the fall season, they will start in maybe a couple of weeks from now. They take the sand here and put it there. And so during the winter, you see a new shape, and the new shape is like this. The new shape is like this. Sorry. Because what they do is they get the sand and bring the sand in a safe position, because they don't want that something like this happens, maybe if you get a violent storm, then maybe that this sand is brought here. What happens after an increasing sea level? If you increase the sea level, you get an increased erosion, and the increased erosion brings the berm into the sea. And the berm is maybe reformed, a little bit shifted landward. What happens with the beach nourishment? So if you have a pre-nourishment profile, is the black thin line, and then immediately after the beach nourishment, you have the profile marked with the thick line, thick black line, and after some time, the waves reshape the beach profile by eroding some of the nourishment, because of course, if you bring sediments there, you stimulate erosion, and then some of the sand is brought into the swash zone or into the surf zone. Okay, and then what happens with if a seawall is constructed? If you get a seawall constructed, and what the shape that you obtain is an excavation and erosion at the toe of the seawall. Why? Because the waves generate erosion at the foot of the seawall, at the toe, and then erosion turbulence, because the waves collide against the seawall and they go down and excavate the sand at the base of the seawall, and the sand is brought a little bit back, is pushed back into the sea. And this is something that can be studied and should be evaluated in order to avoid that, excessive erosion may undermine the stability of the seawall. I just want to give you these figures in order to make you aware of an expectation, in order that you can gain an expectation of what is a qualitative reshape of the beach profile when you make an intervention, when you experience an extreme storm. This qualitative understanding allows you to evaluate also when you make a design if the refined computation of the erosion gives you a reliable result. And I also wanted to give you as an example, but you don't have to learn it by memory, an empirical formula that can be used in order to evaluate when due to a cross-shore sediment transport, erosion prevails on deposition. Just to give you an example of an empirical formula, actually, as I mentioned to you, empirical formulas are much used still much used in coastal engineering. And just to finish, I want to tell you some information. I want to share to you some information on what kind of approach can be used, what kind of formula can be used in order to make a more refined computation of the sediment balance. And what is usually used is this equation, which is the Exner equation. I just want to give you this information because I think it may help you very much to know the terminology. When you listen somebody talking about the Exner equation, it is very simply a differential equation that relates the change in time of the beach profile elevation, h. It is related to the change in space of the sediment flux. And this is a differential equation, meaning that you should apply it at very small spatial and temporal scales with appropriate initial and boundary conditions, because as you see, it's a spatial-temporal differential equation. In order to get the result, you have to integrate over space and over time, like we did with the CRC formula. We cycled over space and over time. And this is a differential equation. It describes changes in the variable of interest, changes in h. Our variable of interest is the beach profile, is h. The differential equation describes changes in the variable of interest, and in order to get the final result, which is h, you need to integrate. And you need to integrate, in this case, over space and over time. And don't be concerned by differential equation and the integrals. They are just differences and sums. An integral is just a sum. It's the simplest operation that we learn at the primary school. Sum. The integral is a sum. So with numerical integration is just adding changes in h. And but they are called differential equations, which means integration, which means initial and boundary condition. Because when you have an equation describing differences, if you want to get the variable, not just the differences, but the original value of the variable, you need the initial condition. You need a starting point. So you need the starting value for h in time and space. Initial condition are starting values in time, time 0, and the boundary conditions are the values at the boundaries of your domain, at the boundary of the space domain. So don't be concerned, but I just want you, I'm not saying anything more. I just want you to know Exner equation, the name, which means the rigorous energy, sediment balance describing the evolution of the beach morphology. The only thing I may ask at the exam is, what is the equation describing, rigorously the differential equation describing beach morphology? And the answer is the Exner equation. You don't need to remember it, even if it's simple, but you don't need to remember it. And so it helps you also to remember that the CRC formula is not physically based. It's an empirical formula. It's similar to a physically based, is almost physically based, but as I said when opening this lecture today, it's an empirical formula. Okay, good. Questions before I pass to the next one, which is simpler. No questions? Okay, before moving to the next one, just give me 1 second. I close R. Okay, and I close this. Good. 1 second. I told you I wanted to show you some videos. What I discuss with you is analytical computation of beach morphodynamics, analytical estimation of the evolution of beach coastline morphology. As you see, there are several assumptions conditioning our computation. And even if you apply the Exner equation, there are, as you may learn, if you expand your knowledge, there are assumptions underlying the Exner equation. And there are boundary conditions, there are numerical approximations, which means that if the system that we have to model to study is very complicated, the approximation may become unacceptable. And typically, it becomes very complicated when the morphology is complicated. When the waves are complicated, we assumed a plane wave. If we admit that there are trains of waves approaching the beach, these methods end up with a severe approximation. So what is an alternative solution? An alternative solution, which is much used in coastal engineering, is what is called physical modeling, which means small scale lab models. I want to show you some examples, some videos which I took at the Deltares in Delft. And the resolution is not really the best because it's you see, this is a huge pool, and I have a better video later. Let me see. A huge pool where they are studying beach erosion. Actually, here it's taken with an old phone. It's 6 years ago. 6 years for a phone, it's very old. And let me see the second one. Maybe the resolution is better in the second. Yeah, it's a bit better. Yeah, there are coastal protections here. They are generating waves against coastal protections in the lab. This is a huge pool. There are, let me see if this is the previous one. See the coastal protection here. Wave. There are other coastal protections up there. And they are studying the resilience of this coastal protection to extreme waves. There are several videos on the web. I make just a quick attempt to find it. Video, Deltares, Delft. Educational videos. There are some of them that are really nice to see. Let's see if it's quick enough. Let's see. Okay, to see the video, one needs to log in. Just a second, because I think some of them. I think this is nice. Okay, let's wait for the. Okay, just 1 second. Skip. You see, this is a wave generator. They are studying the propagation of waves into a flume. This is, if I well remember, the longest flume globally available. They are able to generate very big waves, and they are studying in the bottom up there under the building. They are studying inside the building. They are studying the impact of the waves over a coastal protection. I had a chance to visit the inaugural experiment of this flume. I can tell you that it is scary because it's really a big wave. I think it would be very fun for a surfer inside here.
What about the railway and the
sites. What are they?
What are, sorry? The railway. It is used for, there is what in Italian we call a carro ponte moving over there. It's like a moving train that allows them to put big blocks in the bottom of the flume, you know. And
Is this crazy that you could actually then?
I think they were studying, when I visited, they were studying the resilience, the stability of big blocks, big boulders put on the bottom of the flume. And I don't know which this video, what is about. And this is another experiment. I think it is still Delft. It's a plane wave, you see, and which is moving. And let's see what they are studying at the end of this flume. I don't think it's nothing that has to do with sediments.
It's really long.
Yeah, it's really long. Let's see. This is an experiment. This is, I already saw this. It's an experiment of the impact of a wave against a seawall, if I well remember. Just 1 second. And
Yes, what?
seawall. Yeah. And just 1 second. Let's see. Okay, I move forward, otherwise it's not a seawall here. You see, it's nice, isn't it? Okay. You may learn a lot by looking over the web, looking for videos, and it takes time because it takes time, especially to make the selection. And you know, I was lucky this time, and this is indeed nice because the English is very good; it's well understandable, and also the experiment that they make is really matching our interest today. And yeah. From the chat. It's 12 minutes. Okay. let me make a short break now because I want to invite you and give you 10 minutes to fill the form for the evaluation of the teaching. And you know that we are taking your opinion on the quality of teaching for everybody. So we are taking your opinion on my teaching and then Professor Bratt and Professor Archetti. I am extremely interested in your opinion. So even if you are few students, if you could take just 5-6 minutes now, and you should go to val.unibo.it. So let me just show you. It's val.unibo.it, and then you should put the code here. And the code is 706174. Please let me know if it is working. Let me see what happens if I use the code. Sorry. 706174. 706174. I'm not sure what happens if I put the code. Okay. So there is no verification of the identity, which is fine. This is anonymous, but it is a bit strange that in principle you may.
Can you repeat the code?
The code, yeah. Can you read it? 706174. One thing, there is first part which is numerical. So you just have to select it's a closed answer evaluation. And then there are boxes for text. Please add something, add your opinion in the boxes, because the evaluation of the teacher by the university is done by looking at the statistics of the closed answers. And the boxes are not used for evaluating the professor, but the text is forwarded to me. And I am really interested. I mean, I'm not much interested in the boxes. I am really interested in your suggestions, or if you have any suggestion, any appreciation, because usually, and especially any criticism, please write it there. Okay, I don't know your name. I will see the results next spring. They are not delivered soon. So take just 5 minutes and then we still have half an hour to go. I just leave you alone, so if you want us to discuss, I come back in 5 minutes. You need more time? No. Everything is done. Okay, good. Okay, so 1, 4, 5. Good. I can close this. And now let's here. Monitoring. Let me see if I have a PowerPoint. I don't think so, because this is, yeah, this can be done by looking at the text here. And you don't need to read, of course, but I can select what we are interested in. So now we talk about C-wave recording. C-wave recording is essential to get information on the wave behavior. And the information that is collected is usually stored in databases which are managed by the responsible institutions for the recording itself. These databases are not always open, even if the number of open databases is increasing nowadays, because as you may know, now there is a push also with the national recovery plans in order to promote digitalization of the information and accessibility of the information. So you will find in the future on the web more information with respect to the past related to environment of any type. There is already information available, for instance, on climate projections for the future. There is information available on extreme events that occurred in the past. For instance, there is already a lot of information on the flood that occurred in this region in May. And so it's important to gain the knowledge and the skills to profit from this information. Because today in engineering, it's becoming more and more compelling to make use of innovative information. And this it's on the one hand an advantage, because using more information allows you to increase your reliability, the reliability of your estimations. On the other hand, when more information is available, it becomes more challenging to make the selection of the information and to use it. Because in the past, it was relatively simpler. The information on waves, for instance, was available on papers, and everybody had to use the papers. And the papers provide numbers in a clear way. They are easy to use. They need to be, of course, in the past, they needed to be copied. And for instance, if you want to use it in Excel, you have to copy it, which takes a lot of time, but it's very simple. Today, a lot of information is available in digital form, which it's not as easy to use as the record on paper, because In digital form, the information is stored in different formats. I mentioned to you climatic projections, for instance, and they are stored with a format that in order to get the numbers, you have to interact with the website using a programming language like a Python code. And more skills are needed to get this information. And as I said, also to select it. The advantage of the web is that it allows you to get a lot of information instantaneously. On the other hand, you know better than me that selecting the information, finding the information becomes more difficult, because when the amount of information increases, distilling this information becomes a real skill. So it's extremely important that you gain the skill to look for data. And in order to make the best use of data, you need information on how data is recorded. So you have to understand the difference between a number that is collected with a remote sensor, for instance, or a number that is directly measured. So if you get a measurement of sea level, it's extremely important that you know how it was measured, directly or through a satellite survey, or through the radar, or through what kind of instrument. And you need to be prepared on the uncertainty associated to each measurement techniques. And because this allows you to extract the information from the number. You have to learn what is a metadata. The metadata is information on the number, information on the observation, which tells you how the number was measured, as I said, and may also tell you what is the expected uncertainty, plus minus 5%, 10%, plus minus 20. So it is, in a way, important that you know how the data are recorded. This is why we briefly discussed this in terms of sea waves, how they are recorded. So they are typically recorded, as I said, in public databases, and I will show you a couple of examples. And they are measured with a sensor, sensors that can be divided, can be split into three categories. They can be classified, broadly speaking, according to three categories. Recorders measuring below the sea surface, recorders measuring at the sea surface, and recorders measuring above the sea surface. So let's discuss a little bit what's the difference. So when we talk about, when we talk of recorders measuring below sea surface, we can classify them in two categories. Pressure transducers, so instruments that measure the pressure of water. So the more the height of water over the instrument, the higher the pressure. The instrument measures the pressure. You can call them also pressure sensors. Another category is given by the echo sounders. They are called also inverted echo sounders. So the instruments send a signal from the sea bottom towards the surface. The signal, it's an acoustic signal, which is echoed back. And then the time taken by the signal to reach the surface, to be reflected by the surface back and reach back the instrument, gives an indication of the water depth. And
it's reaching against the instrument that is below.
Yes. So the instrument is on the bottom, and then there is an acoustic signal that is sent up, and it's reflected by echoed. It's echoed by the sea surface and then goes back to the sensor.
It's like a installed instrument.
Yeah, it's an instrument that is fixed to the sea bottom. And keep in mind that sometimes the bottom is fixed because maybe an harbor, maybe usually these instruments are not placed in the open sea. They are placed over a platform, for instance. And they can, given that they can resolve the signal at a very fine time scale, they can detect the oscillation given by waves. What is the advantage of having the recorders below the sea surface? The advantage is the protection given by the coverage of water. They are always in the same condition, same level of salinity. There is little oxygen, so there is also little corrosion. In a way, the body of the ocean, the body of the column of water gives some protection. It is, on the other hand, you understand that these instruments are more difficult to manage because you have to place them over the sea bottom. You have to make sure that there is a connection, either a wired connection or a digital connection. In the past, wires were used. Now, some instruments are able to transmit through a Wi-Fi the observation, but still they are a bit difficult to manage. From a logistic point of view, is easier to use recorders placed at the sea surface or above the sea surface. They are more easily accessible. The recorders measuring at the sea surface are the most used, even today. Some examples. The staffs, and the staffs are, you see the figure, it's clear. It's a ruler. It's a ruler that is fixed typically at structures, or like in this case, it's fixed to the coastline. Usually they are placed over structures. In the past, it was customary, it was usual to take the measurement by visual observation. And of course, visual observation meant that they didn't take observation continuously. They were going there like once a day to take the measurement. So this implies that they were typically used to measure tides rather than waves. Because, you know, waves, it's a frequent oscillation generally.
Are they similar to the one used in the river?
Yes, the same thing. Same thing. And in Italian, it's called asta hydrometrica. It's the same thing. And now there are some of them that are equipped with the float that is taking measurement continuously. So if you, let me see if I can find a sketch somewhere. First search in Italian because I think, yeah, this one. So you see this sketch, it only costs like 600 euros plus VAT. Okay, so you see how it works. There is the stuff is connected to a pipe. There is a pipe close to the stuff. The stuff may be also removed. It's just something aesthetic here. The level is measured by the float, the red ball here. And this pipe is connected to the sea level or the river level, and the float goes up and down. And you may record the position of the float continuously. So it can also measure the oscillation given by waves. Of course, this system has some delay. So if the wave frequency is very high, the measurement may be affected by uncertainty. They typically have a range of frequencies where they optimally work. But it is an instrument that is, as you see, relatively simple and quite reliable. The only thing is that you get a point measurement. It's not distributed. So you cannot put a stuff every 100 meters along a coastline. It's also true that one may say, okay, but the sea conditions don't vary so much. Actually, indeed, depending on the shape of the coastline, the wave behavior can change a lot, even at a short distance. They can really change. If you get into a bay, you have refraction and diffraction. So it's indeed a limitation, the fact that this is a point measurement. And then another recorder at the sea surface that is largely used, a lot used, is the Wave Rider buoy. And here you can see the buoy, the picture of the buoy, and one source of uncertainty is the sea lion that is sitting over there. And of course, these instruments being placed at the sea surface, they have this problem. If there are disturbances at the sea surface, which are instead absent at the sea bottom, if there are these disturbances, it's a problem. And also, you know, it's not so infrequent. Even if you have a staff, you may have like objects colliding against the staff, and therefore, in a way, softening the movement of the waves in the surroundings around the staff. And so this is the problem of these measurements. And the wave, the way the buoy works is through an accelerator that is placed inside. So the buoy goes up and down. And with the accelerator, these instruments can map the oscillation of the buoy. Okay. There are also opportunities to measure from ships. Again, there are sensors that may be placed on both sides of the ship with an accelerator, and then they can monitor both the oscillation of the ship up and down and the oscillation of the seawater. Therefore, they make a kind of difference. And by measuring the height of water on the side of the ship and adding the movement of the ship. These instruments, the Wave Rider buoys and the sensors on the body of the ship are quite expensive instruments. Staffs are less expensive. You have seen the price of a staff. It's not so expensive. I mean, 600 euros plus VAT, it's not much expensive. And most probably there is also included the instrument for sending the data to the database. So it's just a phone connection. It's a connection, a data connection of the type that we use with the phone. So it's really less expensive. These instruments, you know, the accelerometer and also you need the buoy. The buoy is expensive in itself, and also the instruments placed over the ship, they are quite expensive. And also they suffer from the limitation of being a point, providing point measurements. Okay, and they are called over the ship, shipborne wave recorders. They are called here in this way. And there is a mention to the cost. These are expensive instruments. Okay, and let me see if, yeah, okay, perfect. A thing that I forgot to mention, vulnerability to disturbances is to be considered, especially vulnerability by humans, because humans sometimes get fun in disturbing these instruments. And this is a well-known problem, you know. So if you see, if some people, young guys see like a stuff, they can make fun of disturbing the measurement or damaging the instrument. So this is indeed a problem. And also with the buoys, you know, humans can get fun in climbing over the buoy and using the buoy as in order to make fun, to play with the water. And now there is the third category, the third category, recorders measuring above the sea surface. These are increasingly used today, and they are indeed an opportunity because usually these recorders, which we can classify in three types, sorry, but after a while I get tired when I speak in English. We can classify in three categories, and it's cameras or video cameras, radar, and satellites. So these provide a distributed picture of the sea level, which is much interesting. On the other hand, we have to be aware of the limitations. Cameras, and in particular video cameras, are able to provide a continuous picture in time. I mean, continuous in time. It's also continuous in space, but it's also continuous in time. So video cameras indeed allow you to get a video. The video is typically automatically interpreted, automatically deciphered, and therefore you get, at the end of the story, data of wave behavior, wave frequency, wave height, and wave direction. So it's definitely interesting. Of course, they need to be calibrated. They need to be tested. And you have to be aware of the uncertainties. So if during the night they don't work, and also the digital interpretation may be subjected to uncertainty. So you need to get information on the uncertainty of the digital interpretation, which depends on the reliability of the code. Code, I mean the code interpreting the image, and also you need information on the resolution of the camera, because the resolution determines the number of pixels and therefore, at the end of the story, uncertainty. The camera has the advantage with respect to the radar and the satellite of the continuity in time. The radar usually relies on a turning signal, and therefore the signal is reflected by the sea surface back to the radar. So by measuring the time taken to bounce back and measuring the intensity of the signal, reflected signal, the radar gets a picture of the sea. But this picture is discrete because it takes some time to the radar to complete the turning cycle. So typically the resolution of the radar image is like half an hour. Now we have radar that have a higher frequency, but still it's a discrete picture. And can be disturbed by the spray. usually they can take a nice picture, a very detailed picture of the sea surface, and therefore they can indeed detect the wave climate. Satellites. Satellites means getting a picture like this. It's very extended. The time resolution is maybe 6 hours, something like that, because the time step of the picture taken by the satellites, it's not few minutes. It take, as I said, 6 hours or even more. And also the pixels, the spatial resolution, it's coarser with respect to radar. The satellite is much higher and the picture needs to be deciphered. It's really a picture that is taken by the satellite, and by comparing different pictures, they can draw, as you see here, the altimetry, the topography of the ocean, with curves connecting the points with identical altitude. As I said, it's large, and the spatial resolution and the time resolution are a bit coarse, but these are especially useful for quantifying tides, not really for quantifying, as you can understand, the wave height. They measure the height of the ocean surface. They can decipher the motion of tides, the motion of currents, and for this, they can provide indeed a very interesting picture.
That is the sea level surface.
Yeah. It's, and you see the scale. This is Australia. This is South America.
Because the blue one is -10, minus 120.
Let me see, because yeah, there is indeed, it's centimeters.
Okay.
So there is a difference of 2 meters. You know that the ocean, the level of the ocean is up and down. Even at a,
Zero, that is corresponding.
I don't know what is the reference here, but maybe that the zero is the average sea level, maybe. And the average sea level is conventionally computed. I don't remember. If you look on the web, basically they compute the average by making reference to selected measurement points, and they take the average of these. But it does exist a reference zero sea level, of course, because otherwise everything is measured above the mean sea level. Above sea level, it's a mean sea level. Okay, now let me see if these links are still working. Yeah. This is animated figure of ocean topography. It's linked. Let me see this other link, if it's working. I think so. Yes, okay, perfect. Just for your information, they are linked there. Just to close, a few information on the databases. Please have a read at what's written here. And this is a description of the database of the National Oceanographic Service of Italy, and with the location of the buoys and a description of the buoys. This is something that it's relevant for your information, not for the exam, but please have a look independently. And also, there are links to other databases. This is an Australian database. The link, I think, is still working, yeah. And you can play with the data here. You can download data. It's a bit slow, but there is a description on how to download them and what they describe. This is one link that you can explore, and another one is here. It's a map of the wave monitoring sites. If you click over the site, you get you should get a link, a direct link on the numbers. Let's see, with direction, and you see that there is a description of the data, and here you see the graphs. They are taken in real time. Please have a look, because this may be relevant information for you. As a final recommendation, there is a last link, nature-based solution for coastal protection. It's very descriptive and quite short. Please, let me just see. Yeah, please have a look. Have a look, and this can be the subject of very descriptive questions at the exam, like what kind of beach protection nature-based solution strategies you know, and you should mention these ones, cobble burns, and with strength artificial dunes. I don't ask you to go into the details. Beach nourishment and beach scrapping, we already mentioned it. Vegetation recovery. And I please ask you to have a look independently. This is something that is recommended by the university. Very descriptive information can be delivered to the students in the form of independent study. That's it. So, do you have any question? Yeah?
About the exam.
Yeah?
Can we do the exam before Christmas and then after the lesson?
In principle, we are not allowed to make any exam before the end of the lecture period, which is December 19, 20. So before Christmas for sure, but it may be December 20. Yeah, I know. I know, but usually, so formally we are not allowed. We are not allowed to register the exam. The system doesn't allow us to register. And in principle, making the exam and registering later is illegal. But, and